Let's take a look at question 3. 3.1 says, given the geometric series 3 plus 6 plus 12 to n terms, write down the general term for this series. And 3.1.2 asks us to calculate the value for k such that the sum to k from p is equal to 1 for the series 3 over 2 times 2 to the power of p is equal to 89,301. So let's get started with 3.1.1. So in 3.1.1, let's write down the general term for the series. We know that the formula is Tn is equal to AR to the power of n. Let's write that nicely. AR to the power of n minus 1. We know that A is the first term of our formula, which is 3. R is our common ratio, which can be found by taking T2 divided by T1 or T3 divided by T2, and that would be 6 over 3 or 12 over 6, which would just give you 2. So we've got A is equal to 3, T is equal to 2. And we know that the sum for, or the general term for this arithmetic series would be Tn is equal to 3 times 2 to the power of n minus 1. And that's why it's just 1 mark, because you just get 1 mark for substituting 3 and 2 from the terms that have been given. For 3.1.2, we need to find the value of k so that the sum for this series 3 over 2 times 2 to the power of p gives us 89,301. So starting from p is equal to 1, we need to find how many terms in this series are going to give us a sum of 89,301. So let's start off by finding the first term. So our formula is 3 over 2 times 2 to the power of p. So to find T1, that would be where p is equal to 1. So that would just be 3 over 2 times 2 to the power of 1. So that would be 3 over 2 times 2 to the power of 1. That would give us 6 over 2, which just gives us 3. So our first term is 3. Let's find the second term. T2 would be 3 over 2 times 2 to the power of 2. And that would be 3 over 2 times 4. Oops. 3 over 2 times 4. That would give us 3 times 4 is 12, divided by 2 is 6. Our third term would be 3 over 2 times 2 to the power of 3. 2 to the power of 3 is 8, so this is 3 over 2 times 8. And 3 times 8 would be 24 over 2, which gives us 12. So the first 3 terms in our series would be 3 plus 6 plus 12. Sorry. Now, we can take these values that we've just found and substitute them into the formula for the sum for an arithmetic series. So the sum for an arithmetic series is given by Sn is equal to A times R to the power of n minus 1. divided by r minus 1. Now r is our common ratio. Our common ratio is, let's get the highlighter, 2. We already found the value of our first term, t1, which is a, which is 3. And now we can substitute into the formula. So the sum to a certain number, the sum to n, we've already been given as 98,301. So the sum is 98,301 is equal to a, our first term, which is equal to 3, r, which is our common ratio, which is 2, to the power of n minus 1. Everything over r is 2 minus 1. Now 2 minus 1 is just 1. So this is 98,301 is equal to 3 times 2 to the power of n minus 1. If we divide both sides by 3, we'll be left with 27,000, or 32,000 rather, 32,767 is equal to 2 to the power of n minus 1. Now, if we add 1 to both sides, we'll be left with 32,767, or 68, since we're plussing 1, is equal to 2 to the power of n. Now, if we want to find n alone, we're going to have to take the log of base 2 on both sides for each of these numbers. So, to get n alone, that would be n times log of base 2 is equal to the log of 32,768. If we divide both sides by log 2, we'll find that n is equal to 15. Now we know from the sum to an arithmetic series that the value of n is equal to k minus p plus 1. Our value for p from our formula up here starts at 1. We know that n is 15, k is what we're looking for, minus 1 plus 1. 1 and 1 will cancel each other out, therefore k is equal to 15. And that's our solution for 3.1.2. Now, let's take a look at question 3.2. In question 3.2, we're told that a geometric sequence and an arithmetic sequence have the same first term. So, we can have arithmetic sequence on one side and we can have our geometric sequence on the other side. And write down all the information that we have for both of these sequences. We're told that they have the same first term. So we know that T1 is equal to A, and for the geometric sequence, T1 is also equal to A. We're told that the common ratio for the geometric sequence is 1 over 3. The common ratio is given as R, so R is equal to 3. The common difference for the arithmetic series is given as 3, so D is equal to 3 for the arithmetic series. We're told that the sum of 22 terms of the arithmetic series is 734. more than the sum, so it's plus 734, then the sum to infinity of the geometric sequence. So we can write this by making the two equations for an arithmetic sequence and a geometric sequence equal to each other. So the sum to 22, or the sum for an arithmetic sequence, would be given as n over 2 times 2a plus n minus 1 multiplied by d. And we know that the sum for a geometric sequence is a over 1 minus r, and we're told that the geometric sequence, the sum of the 22 terms is 743 more than the sum for a geometric sequence. So this is plus 734. Now if we substitute n in this equation, we know that this is the sum to 22. So this is 22 over 2 times 2a plus 22 minus 1 times the difference we found is 3. And all of this is equal to a minus 1 over r plus 734. Now we need to simplify this. 22 divided by 2 gives us 11. 11 times 2a plus 22 minus 1 is 21. 21 times 3 gives us 63, is equal to a over 1 minus r, we said, is 1 over 3. So mistake over here. R is 1 over 3. So we substitute 1 over 3 into this equation plus 734. 11 times 2a gives us 22a plus 11 times 63 gives us 693 is equal to a divided by 1 minus 3a is going to give us 3 over 2a plus 734. And if we bring all the a's to the left hand side, we have 22a minus 3 over 2a. And if we take 693 to the other side, we'll have 734 minus 693. And 22 minus 3 over 2a is going to come up to a is equal to 2 if we simplify this on our calculators.